Welcome to our Keys Explore on how we can hunt for dark matter. My name is Jacob. Since we were young, we've always had a passion for learning more about our universe.
Hey, my name's Frank, and we thought that this Keys Explore was a great way of expressing our passion for physics and really pushing our knowledge in this area of physics.
I'm Oscar. I take maths, chemistry, physics and further maths, and I'm planning to do a maths degree next year. And I'll let Frank start off our video.
In 1933, Swiss physicist Fritz Zwicky was analysing data from a group of galaxies called the Coma Cluster. After measuring the orbital speeds of these galaxies, he found that several of them were moving far faster than he expected. He theorised that the galaxies were being accelerated gravitationally by some invisible mass which he named Dunkel material,
Which, surprise, surprise, translates to dark matter.
He came to this conclusion by first estimating the mass of galaxies using the virial theorem. This says that for a collection of bodies moving in a gravitational field, they're in an equilibrium configuration, which means that the system is not expanding nor contracting. The total kinetic energy and potential energy, K and V respectively, are related by 2K plus V equals 0. Here we will say that the system we are describing is a galaxy cluster, like the one that Fritz Zwicky was analysing. We note that the mean square velocity of the galaxies in a galaxy cluster, which I've given here as the velocity dispersion, is equal to the sum of the mass of a galaxy times by the velocity squared, divided by the sum of the mass of a galaxy. We can say that this has the same form as half mv squared, but we've times it by 2, so we can say that this is equal to 2 times the kinetic energy of the galaxies. This is divided by the mass of the galaxies. And then I'll just write this as 2k over m for simplicity. Each particle feels a gravitational force from all others, and the total potential energy is given by V equals minus gm squared over r subscript e. This is where r subscript e is the effective gravitational radius that must be estimated. This can be done, for example, by measuring the average separation between galaxies. We can now use our term for the velocity dispersion and our term for the total potential energy to find the velocity dispersion in terms of g, m, and re. And the way we do that is first by rearranging our velocity dispersion equation. We get that the velocity dispersion times by m equals 2k. And we can also we can see that this velocity dispersion is equal to 2k, and this 2k is in our virial theorem. So we'll sub this into our virial theorem. We've also got our total potential energy here, which is also in our virial theorem. And so we'll rewrite our virial theorem as such, with the velocity dispersion times by m minus g m squared over re equals 0. Now I'm going to add this term to both sides, and I'm going to write that over here. I've got the velocity dispersion. What I'm also going to do is I notice that both terms are being times by at least a power of m, so I'm going to just cancel those out. Velocity dispersion is equal to g, and we've cancelled one of these powers, g m over re. The velocity dispersion is estimated through measuring the standard deviation of line of sight velocity distribution of the galaxies in a cluster. Note that when we measure the galaxies' velocities, we measure them through their redshift, and this only gives us a line of sight component of their velocity. I'll let Oscar explain right now how we measure their line of sight velocity.
So how we measure the velocity of these galaxies is through diffraction gratings. So light from these galaxies will be emitted and we pass this through a diffraction grating. And from this, we can form a absorption spectrum with blue light with the lowest wavelength on the left and red light with the highest wavelength on the right. And this will not be a continuous spectrum. So from these gaps, we can find out what elements these are. And we can compare that spectrum from when these elements are moving at very high speeds in these galaxies, and we can compare them to the normal absorption spectrum of them stationary on Earth. And what we find is with the absorption spectrum from far out galaxies, these little gaps that we identified all actually shifted to the right, which is why it's called redshift, because everything is shifted to the right, which is the more red wavelength. So this phenomena is called the Doppler shift. And because all of the absorption spectrum is shifting to the right, this tells us that the far-away galaxy is actually moving away from us. And this shift is caused by the light becoming more elongated and stretched due to this galaxy moving further away. So how does this let us find out the velocity of these galaxies? Well, because this absorption spectrum has a measurement of lambda, we can compare the absorption spectrum of the element when it's moving at high speeds in this galaxy, and we can compare that to the value of lambda of these spaces when stationary on Earth. So if we find the difference between these and divide it by the frequency, this gives us a proportion. And this proportion is approximately the same as the recessional velocity divided by the speed of light. I say approximately because when you get to velocities that are close to the speed of light, the boundary between mass and energy kind of becomes grey. But roughly, we can set these two equal to each other. So delta lambda over lambda is equal to, let's say, the recessional velocity v over the speed of light. So if you times both sides by the speed of light, you get the speed of light times the change in wavelength, all divided by the wavelength, and this will be equal to your recessional velocity.
When we measure this velocity, we cannot know any other speed they have in any other direction. However, on average, the velocity will be the same in the plane of the sky as it is in the line of sight. So, using that and our previous equation, we can find the velocity dispersion in terms of the line of sight velocity, and then rearrange to estimate the mass, which I'll show you how we do it in a second. So here's our previous equation that I showed how we got to before, and here's our velocity dispersion. And we said that this is equal to, given our estimation, that it's 3 times the line of sight velocity squared. That's because it's 3, not root 3, as we're squaring the velocities. And so we can use this in this equation. So we get 3 delta. And then we can times by RE and divide by G. Now this gives us an estimate of the mass. And this is how Fritz Zwicky estimated the mass of the galaxies in the Coma cluster.
This was initially lost to time, 40 years later when the hypothesis of dark matter began to gain traction. The idea of clouds of unseen matter was theorised simultaneously in both Tartu, Estonia and Princeton University. Vera Rubin and Ken Ford gathered more evidence to back up this hypothetical matter by finding the rotation curve,
which is a plot of a star's orbital speed against its radial distance,
of spiral galaxies, including our galactic neighbour, the Andromeda Galaxy.
Okay, so we know from circular motion that the centripetal force is equal to the mass times the velocity squared times the radius of the path. And because, so if we have a big body in the middle, the planet will orbit it in a roughly circular pattern. And from Newton's laws of gravitation, we know that this force is also equal to the mass of the big planet in the middle, I think that is big M, and then the little planet, which is little m. So, and this timed by gravitational constant, and it's divided by r squared, which is this distance here. So if we set these equal to each other, we get big M g over r squared is equal to mv squared over r. These masses just cancel. If you times both sides by r, you get mg over r. It's just equal to v squared. And because the mass of the planet, and this is just a constant, you can just label that as k. So k is equal to r equals v squared. And therefore 1 over r is proportional to v squared. So you can think of this as this little mass as like a star, and this big mass is like the centre of a galaxy. So based off this proportion, you expect this kind of graph when you plot against velocity against radius. But actually, it turned out to be something like this. So this begs the question, what is accelerating this matter? And it's actually due to dark matter.
They found that the velocity of stars inside these galaxies did not match their predicted speed using a model of the galaxy, with a known distribution of visible matter in the galaxy. They predicted that the ratio of visible to dark matter in these spiral galaxies was about a factor of 10. She said that this was also a good number for the ratio of our ignorance to knowledge in the realm of dark matter. We're out of kindergarten, but only in about 3rd grade.
These progressions really catalysed the global hunt for dark matter, and since then multiple dozen of experiments have been done by many organisations around the world, such as King's College London, who published a paper on March 10th this year. They published a study on analysing the mysterious ionised hydrogen in the CMZ. They said that it could point to a different, less massive form of dark matter than the most commonly accepted WIMPs. This would allow dark matter to be potentially detected by its chemical effect on the universe. The form of dark matter proposed would be one where 2 dark matter particles would annihilate and emit an electron and a positron. This would account for the ionization of the hydrogen, which isn't explained by current models of cosmic rays and other ionizing beams that we currently know of. Scientists look to verify this with more data, which looks at a more precise mapping of ionization throughout the CMZ, which will likely be provided by NASA's Compton Spectrometer and Imager, or COSI, which is very sensitive to gamma rays, which we compared to the predicted levels of the model of ionization in the CMZ. Other galaxies are being looked at, as this effect should not be solely attributed to the Milky Way, but other galaxies as well. Skeptics argue that alternative explanations such as unknown cosmic ray sources could be used to explain the ionized hydrogen. However, the dark matter beautifully explains the phenomenon.
Another useful way of detecting dark matter is with gravitational lensing, and it stems from a lot of the ideas theorised by Einstein, and stems from general relativity, where massive celestial bodies actually bend space-time, and light rays can be affected by this bending, causing distorted images that we receive from our telescopes.
So what happens is, when you have a light source, light is emitted radially, so in all directions. And some of the light which travels, at an angle, so not along this straight path, but at an angle. Actually, because space-time is being curved, the light follows a straight path through curved space-time. So actually, if you were to imagine it, it would follow like a curved path. As such. And so you get light which travels in a straight line following this curved path, and when we get these curved paths, we form, from our image in the sky, we form these are Einstein rings, where these are like distorted images of this light source, and this is the heavily massive object which is bending space-time, allowing these to happen. We can measure the mass of these.
So why is this relevant to dark matter? If we can measure the amount of matter via the Einstein rings, then we can compare that to the visible mass and thus find the mass of the dark matter, which causes this discrepancy.
You might wonder what the structure of dark matter might look like on a large scale. Well, they exist in big halos around galaxies.
Even the earliest simulations of structure formation in a CDM
Cold dark matter.
universe emphasize that halos are substantially flattened, giving them an ellipsoidal shape, kind of like a huge Mentos surrounding this central galaxy. They're given the name halo because they completely engulf the galaxy that they surround. So let's look at our possible candidates. First, we have WIMPs. Now, it's not very nice, but their name stands for Weakly Interacting Massive Particles. It's kind of self-explanatory. They're particles with a mass, obviously, and they interact through the weak nuclear force, but very, very infrequently. They are the leading candidate of dark matter, and they're the most popular candidate among scientists, and we're currently trying to detect them in experiments such as Dama Libra in Italy. It's about a mile on the ground. It's very impressive. They are using sodium iodide crystals submerged in linear alkyl benzene surrounding a meter of concrete, and they're trying to detect interactions between the dark matter particles and the particles in the sodium iodide crystals, and they're measuring the light that comes out. So far, the lack of detection has set a lower limit on the mass and hence the energy of the dark matter particle, and that limit is about 100 giga-electronvolts. This is because as the particles get more massive, you expect them to be more reactive because they're larger. So because we've not had much detection or any detection at all, they can't be so big. The LHC at CERN may be able to create dark matter particles depending on their mass and provide an improved and underlying framework of particle physics within which dark matter is better understood.
Now, it is worth noting WIMPs are a particle which are theorised through string theory, and so require supersymmetry to exist.
Another candidate is axions. These were originally particles which were proposed to solve the strong CP problem, which uses the oscillation of theorised quantum properties to create a new particle, which would simultaneously solve the dark matter problem.
Again, we return to CERN, where they're building an axion telescope, which is looking straight into the sun and seeing if they can find evidence for axions.
Sterile neutrinos are another candidate. However, dark matter needs to be cold or slow moving to form halos around galaxies as they do, which neutrinos are not, so these are an unlikely candidate. The last one we'll mention is emerging gravity. As unlikely as it is, some scientists predict that maybe we have misunderstood gravity and thus we need a new model, or even an adjustment to the current one.
However, this would go against the mountains of evidence we have for general relativity.
Although progress to date may seem slow, we still have confidence that we can gradually put together the pieces of the complex puzzle that is dark matter, and eventually find these pieces, whether it's through the use of a particle accelerator, an experiment deep in an Italian gold mine, or looking into space with a massive telescope.
In the words of Andrew Chudevsky, it took nearly 50 years to find the Higgs boson, but we've only been looking for dark matter for 30 years.
However, we also have to address the concept that weighs heavy on every astrophysicist's mind. Can we even find it? It doesn't interact with photons, and we haven't detected it via the weak nuclear force for certain. Then maybe it will elude us for good.
So, since it's so hard to find and might not affect your day-to-day life, then someone, other than you or me, may question why this all matters.
Well, the understanding of our universe has piqued human interest since our dawn. We are always striving to find and search for the impossible.
But hey, maybe you're boring and don't care about that kind of stuff. But who knows, maybe, just maybe, dark matter is the key to unlocking a whole new advanced society. I guess we'll just have to wait and see.